So as Charlotte said, my name is ElsaNystram. I'm a PhD student at Applied Geochemistry at Luleå Technical University. I'm here to present the project Utilization of Industrial Residuals for Prevention of Sulfide Oxidation in Mine Waste, or as I prefer to call it, STOPOX. It is financed by Vinnova and Boliden, but we also have different project partners representing materials or other knowledge that they have. So the purpose for this sub-project within the project I just described is to develop techniques for prevention of sulfide oxidation in mine waste. And this would then lead to an improvement of the leachate quality during mining operations. So the specific objective is to evaluate different inhibition techniques used from both economical but also environmental and technical perspectives. Within this project, our focus is on industrial remnants from other industries. So, a little bit about the problem. We are working with sulfidic mine waste that has been selectively chosen for its high sulfide content, which means that it is not representative for any mining area. This waste rock has an abundance of sulfide minerals, which means that they're acid producing, and has a low content of buffering minerals, which means that they have the possibility to, or they can generate something called acid rock drainage. And as most of you know, that is characterized by low pH, it has a high metal and metalloid content, as well as sulfide content. So traditionally, this acid rock drainage is limed during operation in order to rid of these metals and metalloids and increase the pH. What we propose is that instead of liming this drainage, you should apply these buffering minerals to the waste rock heaps themselves. And this would then create an environment where coatings are formed on top of the sulfide, which would then prevent the sulfides from oxidizing. So this would then lead to a decrease in metal and metalloid concentrations, as well as sulfate release in the drainage. Moreover, if we use industrial residues instead of virgin products such as lime, we could decrease the cost for buffering minerals as well as energy and also sludge treatment. So what we've been doing is that we've studied different industrial residues and byproducts such as blast furnace slag, both air-cooled and water granulated. We've looked at cement kiln dust, lime kiln dust, as well as fly ash. What we've been doing is that we've been adding this in small-scale laboratory test cells on top of waste rock, not compacted, but loosely sprinkled over. And the reason why we've been looking at industrial residues and byproducts is primarily because it has a lower material cost, as well as it has limited or sometimes actually no use. So some of the results. I've chosen just to show you a summary of a table containing information from the last 2 years of leaching. So as you can see, at the top you have the waste rock concentrations, average concentrations from day 400 to 700. It is characterized by a very low pH, and we have very high concentration of both metals and metalloids as well as sulfur out. If we compare those results to lime kiln dust, addition of 5% as well as fly ash, addition of 1 or 2.5%, we can see that both metals and metalloids are decreased dramatically, as well as sulfur. I don't think it would be fair to say that we have a decrease of 99%, as the decrease sometimes, as you can see, is 1,000-fold or more. So these are the materials that have shown best results so far, and yes. So future activities. Well, the results indicate that we have some sort of coating formed, and now we want to identify these coatings. What are they made of? how they have the ability to incorporate trace elements in their matrix. And also, of course, do some type of long-term evaluation of both the butter quality, but also the stability of these coatings. Thank you.